So this recorded lecture picks up on the discussions that were made before. Okay. So the last time we were on the topic of lossless source coding theorem, in which we have defined the first fundamental limit that we have to surpass in order for, or we have to comply with, in order for us to make a reliable transmission over a communications an electronic communication system. Okay, so this limit is essentially concerns about the transmission rate of the message and the entropy of the source. So we have already mentioned that this limit should be we have already mentioned that the transmission rate of the message must be greater than or at least equal to the entropy of the source. Now, we are on the part where we have already discussed yung mga requirements natin with regards to the codes that we wish to synthesize for our source. Okay. The thing is that we have just mentioned them as qualities or characteristics. Okay. At this point, we would like to quantify them or put them into numbers para mas ma-characterize natin siya ng mas methodical. Okay? So, in this case, at this point, we will introduce yung tinatawag nating Kraft inequality. Okay? Or in some books, this one, okay, is also termed as the Kraft-Macmillan inequality. Yun. Okay? So, our main objective is to devise a systematic procedure for constructing uniquely decodable variable length codes that are efficient. Okay? So, variable length codes that are efficient in the sense that the average number of bits per source letter. Okay, again, let me remind you, this bits does not, again, pertain to the bits of a binary code word. Okay? It pertains to the amount of information contained in a message. Hindi ito yung bits, again, that pertains to the binary digit of a code word. Okay? So, we would like to design, okay? Our main objective for the design of the algorithm that would generate our source code would be it would be uniquely decodable. Okay? It would be uniquely decodable. It is efficient. Okay? And efficiency would be defined in terms of the number of average bits, the average number of bits per source letter, which we will define as the quantity here. Okay? Now, notice the symbol here as R bar. Okay, not R. Okay, so in the statement of source coding theorem, lossless source coding theorem, ang ginamit nating limit o ang ginamit nating quantity doon, okay, is transmission rate, which is R. Okay? In this case, we will use instead the kasi ang problema kasi with R, the transmission rate as a quantity, okay, is that it actually involves time kasi nga rate siya. It's a rate of change quantity. So therefore, we should have a sense of the number of or the amount of information that we have to transmit over time. Okay? So let's use a quantity that is not dependent on time. Okay? So instead, let's specify that quantity to be in terms of the average number of bits per source letter. Okay, which is computed as this one. Okay? So we would like this R to be minimized. Okay? Because we would like it to be minimized kasi later on we will be able to discover that the closer the R bar, okay, to the entropy, okay, the more efficient the code. Okay? So although uh so remember that we have specified the source lossless source coding algorithm limit as your transmission rate should be greater than or equal to the entropy contained in the source. Okay? This would also we would provide later on another statement of this limit. Pero in terms naman of of the of R bar or the average number of bits. So ang magiging statement natin diyan is almost the same. That is R bar should be greater than or equal to the entropy of the source. Okay? So while we would like the average number of bits to be higher, okay, than the entropy, kasi that is where transmission would happen eh. Okay? Remember that transmission is only possible sa isang digital communication system if this first limit is surpassed. Okay? But we would discover later on that codes would be more efficient if this R bar is actually close to the entropy. Yung pagiging malapit niya sa pagiging equal nila. Okay? So there. So the closer the R bar to the entropy, the more efficient the code is. Okay? So the Kraft-Macmillan inequality, okay, states that a necessary and sufficient condition, okay, a necessary and sufficient condition for the existence of a binary code, okay, with code words, okay, having lengths n1, n2, up to nl, okay, in which you would notice that the the lengths of the code words here are arranged in increasing order. So N1 is less than N2, N2 is less than N3, N3 and so on would be less than NL. Okay? Now, so this condition, the Kraft inequality, if satisfied, okay, is said to pertain or is said to if code words, okay, parang ganitong statement. If the code words, okay, or the binary code words satisfy, okay, satisfy this Kraft inequality. So let's call it KI, the Kraft inequality. Okay. It turns out that these code words also satisfy the prefix condition. Okay, it will also satisfy it can also satisfy the prefix condition. Again, ang ang keyword doon is it can. Okay, it can satisfy the prefix condition. Okay? Kasi what the inequality measures is actually yung length of each code word representing each message. Okay? Ngayon, you may be able to specify yung tamang set of lengths for each of the code words or for all of the code words in a given set of code. Okay? Pero it doesn't necessarily mean na yung mismong code ay magsasatisfy ng prefix condition. Basta ang sinasabi natin dito, what we are trying to say here is that if the Kraft inequality is satisfied, prefix condition can also be satisfied. Okay? So, the Kraft inequality, okay, is useful for checking if there exists a prefix code within a given set of code word lengths. So, kung meron tayong set of code word lengths, we would be able to check using the Kraft inequality. We would be able to check, okay? We would be able to check use Kraft inequality, okay? To check if a prefix code or if the prefix condition can be satisfied given the set of code word lengths. And that code word length is NK or NL, sorry. NL. Okay? So, mati-check natin ngayon kung yung set of code word lengths, okay, will be able to generate a code that satisfies the prefix condition. Okay? Pero yung if for example, meron na kayong naka-design na code, tapos alam niyo na yung code word lengths ng bawat isang code. And then chinek nyo, okay, chinek nyo using the Kraft inequality whether it is whether the Kraft inequality is satisfied or not. Okay? It is possible that the Kraft inequality is satisfied for the given set of code word lengths. Okay? But it may also be possible that kahit na nagko-comply yung code mo sa Kraft inequality, okay? It is possible na yung mismong code mo is not compliant with the prefix code. Okay? So we can only check, okay, if a prefix code or if the set of code word lengths can generate a code that satisfies the prefix condition. But for the generation of the prefix of the codes that satisfy the prefix condition themselves, it's another matter. Okay? So ayun. Now let's take a look at example 8, in which we will consider 5 different source codes proposed for a memoryless source X, okay, with 4 elementary messages. So our source has 4 messages, A1, A2, A3, and A4. Okay? And then there are 5 codes, okay, designed for such source. Okay? So let's try to determine the Kraft number. Okay, let's call this yung left side ng Kraft inequality. Okay, yung left side ng Kraft inequality. Let's call it as the Kraft number. Okay? So let's determine the Kraft number, this one. Okay? And let's comment on the results. Okay? So for code A, okay? So taking a look at code A, let's count the number of let's determine the length of the code words for each of the message. So kung ilang binary digits ang nandun sa code word, okay, ng isang message. So message A1, ito, A1, A2, A3, and A4. Each of these have 2. Okay, so ito yung NL bale. Okay, or NK. NK pala to. Sorry. So NK. So this has 2 binary digits. This has 2 binary digits. 2 binary digits and 2 binary digits. Okay, so therefore, the set of code word lengths, okay, this is what we call now the set of code word lengths. Okay. This is the set of code word lengths, okay, NK. So we can write it as a set. Now we will use that to compute the Kraft number. So we will have to substitute it in this formula. Okay? Substitute natin dyan sa formula na yun. Okay, so that would be simply 2 raised to negative 2. Okay, so 2 raised to itong negative na to, yun, negative. Tapos 2. Okay? Plus 2 raised to negative 2 plus 2 raised to negative 2 and so on. So that would be equal to 4 times 2 raised to negative 2. So that's simply 1. Okay? So yung yung Kraft number natin for code A is 1. Okay? So that's the Kraft number for code A. Now for code B, so this is your code B, okay? So we determine the code word lengths for each of the code that represents your message, okay? So this is your NK. So yung first code nyo is represented by 1 binary digit of code, and then the rest are represented by 3 binary digits of code. So the set of code word lengths that we have is this one. So 1, 3, 3, and 3. So we use now this formula to compute for the Kraft number. So we have 2 raised to negative 1 plus 2 raised to negative 3 plus 2 raised to negative 3 plus 2 raised to negative 3 and so on. So that is computed as 7 over 8. So therefore, for code B, the Kraft number is 7 over 8. Okay? Now, let's continue on with code C. Okay? So, for code C, we determine the code word lengths. Okay? So, we have here NK. So, the first code word has 1 binary digit of code. The second one has 2, and the rest have 3. So, this is the set now of your code word lengths. So, to compute the Kraft number now, we use again the formula. So, we'll have 2 raised to 1 plus 2 raised to 2. 2 raised to negative 1 plus 2 raised to negative 2 plus 2 raised to negative 3 plus 2 raised to negative. That gives you 1 as the Kraft number. So, for code D, we again determine the set of code word lengths. Okay? So, we have, for the first code, we have 1. Then, for the second and third code, we have 3 and 3. Okay? And then, for the third code, we have 2. Okay? So, we have the set of code word lengths as 1, 3, 3, 2. And as you can see, this is actually essentially the same as this one. Okay? The same as code C. Okay? It's just that magkaiba lang ng arrangement ng code word lengths. Pero essentially, pareho lang yan. So, 1 din yung lalabas na Kraft number niyan. Okay? Or Kraft Macmillan number. And then, finally, for code E. So, these are the codes for code E. And we generate or we determine the code word lengths for each code. So we have here 1, 2, 3, 3, and 2. So those are the number of binary digits for each of the codes. So we have the set 1, 2, 3, and 2. So we compute now, okay? We compute now the Kraft Macmillan number for code E, and it turns out to be 9/8. Okay, now let's comment on the results now. Now, first we take a look at code A and take note that code A is constant length. It's a fixed length code. Okay? So the code words are have constant length. Okay? So if since there are four messages, and each code has two binary digits. So we are sure that each message would get their own code. So therefore, each of those code is unique. So this code is a unique code. Okay? Now, this is also decodable, uniquely decodable without delay. Essentially because since this is a fixed length code, the decoder would only expect 2 bits. Okay? And then from there, can now decode. Pwede na siya mag-decode pagkatapos ng 2 bits kasi alam niya 2 bits lang naman lahat ng codes niya. Okay? So therefore, uniquely decodable yan without delay. Okay? So, yun ang alam natin kagad sa fixed length codes. It's uniquely decodable kasi nga fixed yung length niya. So the decoder would be able to make a decision, okay, after nung ilang bits, okay? And if tama yung pagkakadesign ng code, it's unique also. So, ang titingnan natin dyan is that the length of the code word should satisfy yung 2 raised to b na criteria, where b is the number of binary digits of the code word. Okay, so yung L dito is the number of messages of the alphabet. And this is for fixed length code to. This is for a fixed length code. Okay, so since apat yung messages niyo, okay, A1, A2, A3, and A4, then meron kayong dalawang binary digits for each of the code. Then this is satisfied. So therefore, unique yung code natin. Also, remember or recall that the Kraft Macmillan number for code A is actually 1. Okay? Which now satisfies yung Kraft Macmillan inequality. Okay? So again, the Kraft Macmillan inequality or the Kraft inequality states that, okay, the Kraft Macmillan number, okay, ito yun, yung Kraft Macmillan number or KM number, okay, should be less than or equal to 1. Okay? So since this is 1, we say that the Kraft Macmillan inequality is satisfied for code A. Okay? Which is the case naman for all fixed length codes. Okay, it would fixed length codes will always satisfy the Kraft Macmillan o the Kraft inequality. Lagi 'yan. Okay? Kaya lang ang problema lang talaga sa fixed length code is that is yung inefficiency niya. Okay? So, dahil nga sa hindi siya naka-base sa probability, it tends to be inefficient in terms of transmission. Okay? Now, let's move on to code B. Okay. So we see that the Kraft number that we have computed for code B is 7/8. Okay. So we recall that we are able to compute 7/8 as the Kraft number for code B, which is less than 1. Okay. So therefore, code B also satisfies the Kraft inequality. Okay. So code B fulfill or satisfies the Kraft inequality. Okay. And also, as you observe from the code, okay, since yung last three codes ni code B are three binary digits. Okay. It also satisfies yung prefix condition natin. Actually, it's almost the same as this one. Okay, it's almost the same as this one. Okay. Yun nga lang, ang isang lang dito, ang isang medyo wala naman masyadong issue with code B. Okay. So, yun nga, mas mahaba lang yung codes na ginagamit niya for the rest of the messages compared to code A. Okay. Pero actually yung characteristics ng code ng code B is almost the same as the characteristics of code A. So, meaning this is also uniquely decodable. Okay. Without delay. Kasi pag na-encounter mo kasi yung 0 as a code, okay? Alam mo na made-decode mo siya sa A1 kapag nag-iisa lang yung nakita mong 0. Pero pag may naunang 1 diyan, okay? It means that you cannot decode the next 0 as an A1. Okay? In fact, kapag ka 1 0 ito, okay? Without actually waiting for the third bit, okay? The decoder can actually outright, dalawa pa lang to can outright decode it to A2. Okay? And kapag ka na-receive naman niya yung code word na 1, 1 at the start, then yun, kailangan niyang hintayin yung third bit. So, kasi kapag ka nag-0 yan, tsaka niya lang madedecode yan to A3. Or kapag ka nag-1 yan, tsaka niya lang madedecode to A4. Pero still, kapag ka ang lumalabas sa code niyo is yung 0 ay may kasunod na 1, this is not to be the decoder would not confuse this to be for A1 kasi may naunang 1 sa kanya. Okay? So therefore, this is uniquely decodable. Okay? So it also implies that it satisfies the prefix condition. Okay? But tatandaan natin again. The Kraft inequality, okay, tests whether code word lengths, okay, can result in a code that satisfies the prefix condition. Okay? But even if yung code word lengths mo nagsasatisfy ng Kraft inequality, pero mali pa rin yung design ng code mo, okay, then maaaring mag-violate pa rin siya ng prefix condition. Okay? So, hindi siya parang hindi, if Kraft inequality is satisfied, okay, if Kraft inequality is satisfied, it doesn't really follow agad, okay, that prefix condition is satisfied. Okay? It does not follow agad. Okay? More of like parang if the prefix condition is satisfied, okay, if the prefix condition is satisfied by your code, okay, then the set of code word lengths, okay, the set of code word lengths satisfies the Kraft inequality. Okay? So remember that the Kraft inequality just tests, okay, whether it is possible to have a prefix code for a given set of code word lengths. Okay? So yun. Now let's take a look at code C. So we see that the code word C satisfies the Kraft inequality. Okay, it satisfies the Kraft inequality. And observing the code words themselves, okay, these codes also satisfy the prefix condition. Okay, So, wala naman tayong makikitang prefix dito kasi ito is not a prefix of any of the succeeding codes or longer codes. So, yun. So, C is uniquely decodable, okay, and satisfies the Kraft inequality. Okay. So, now let's proceed with code D. So, we have noted na yung set of code words, code word lengths for C and D pareho. Okay, so that is 1, 2, 3, 3. Ito naman, ganoon din. 1, 3, magkaiba lang ng arrangement. So, 1, 3, 3, at saka 2. So, pareho sila ng set of code word lengths. Okay? So, we take note that both of them would satisfy the Kraft inequality. So, code C and code D would both satisfy the Kraft inequality kasi pareho ng magiging Kraft number yan. Okay? Or Kraft Macmillan number. Okay? But here's the thing. Ito yung sinasabi ko kanina pa, that the satisfaction of Kraft inequality does not really follow the satisfaction of the prefix condition. Okay. Kung titingnan niyo yung pagkaka-design ng codes ng code T, nagva-violate na to ng prefix condition. Okay? So, itong code kasi na to, itong 1-1 na code na to, okay, is actually found on a longer code. Okay? It's actually found on a longer code. So, therefore, this code violates, okay, this is a prefix code. This is a prefix code. Okay, so this violates the prefix condition. So therefore, this is a code that can be decoded pero kailangan ng that would cause considerable delay. Okay, so again, ang sinasabi natin, given na meron kayong set of code word lengths, okay, kahit na pareho yan, okay, kung sablay talaga yung pagkaka-design ng code ninyo, okay, it would still lead to a code that violates the prefix condition. Okay, even if the set of code word lengths leads you to think that it satisfies the Kraft inequality. Okay. Now, finally, if we remember in code E, so hindi ko nilalagay yung code E dito, that the Kraft number for code E is 9/8, which is more than 1. Okay, so therefore, the code the set of code word lengths for code E, which is was determined to be 1, na-determine natin yun as ito, 1, 2, 3, 2. So 1, 2, 3, 2. Or say, isusunod natin 1, 2, 2, 3. Okay. So, given this set of code word lengths, hindi kayo makakapag-design ng code nito kapag ito yung ginamit yung set of code word lengths para sa design ng codes ninyo. Okay? You would not be able to design any code that complies with the prefix condition. So, hindi kayo makakapag-design ng kahit anong code. Basta yan yung set of code word lengths. Okay? So, yun ang natin. Yun ang titingnan natin with the Kraft inequality. Okay? We can determine or we can predict, okay, using the set of code word lengths, okay, if a code that satisfies the prefix condition is possible. Okay? Pero again, it is up to us to actually design a code. Okay? It is actually up to us to design a code that is compliant with the prefix condition. Okay? Okay. So, in example 9, let us attempt to design or synthesize a code for a 5-element alphabet. So, ang messages niyan is A1, A2, A3, A4, and A5. Okay? Now, here's the easiest way, okay, to construct a code or synthesize a code that would comply with the prefix condition. Okay? So, this is also under the assumption that the alphabet is arranged, okay, is arranged such that, okay, the probability of A1, okay, is greater than the probability or equal to the probability of A2, okay, and is greater than or equal to the probability of A3, greater than equal to probability of A4. Kumbaga, the elements or the alphabets are arranged in such a way that the probability of their occurrences is decreasing. Okay? So, yun yung assumption natin lagi. As actually, when you are to design a code, that's actually the first task that you have to do. Arrange the alphabet in terms of decreasing probability of occurrences. Okay. So, what would be the easiest way to synthesize a code for this alphabet, for this source? Okay. Since A, okay, would be the most would be the message that is most probable to occur. Okay. We would like to assign it with the shortest code possible. So let's assign a one binary digit for its code word. So let's use the symbol 0. Okay, for message A1. Okay. Now, moving forward, in order for us to make sure that the symbol or that this 0, okay, be not a prefix of another code word. Kasi magpe-prefix to kapag yung next code word natin, sinimulan din natin sa 0. Or any other longer code word na gagamitin natin, isisimulan natin sa 0. Okay, so therefore, para maiwasan natin yung violation sa prefix condition, kung 0 yung ginamit nating symbol para sa first letter natin, then the next message natin should begin with a 1. So dun pa lang nakatawid na tayo sa prefix condition. Okay? Now let's pero wag lang yung 1 kasi baka naman mahirapan naman tayo dun sa mga susunod kasi after that the only choice that we will have is to use 1 and 0 para simulan siya. So we cannot choose or we cannot assign the symbol 1 only. Okay? For A2. Rather, let's assign the symbol 1 0. So that we would still be allowed, okay? We would still be allowed to use yung symbol na 1 0. Okay? We would be able to think of other symbols pa for other messages. So dito nga since 1 0 yung in-assign natin para hindi siya maging prefix ng iba pa, then the remaining code words will have to start with 1 1. So A3 nga gagawin nating 1 1 0. Okay? Then yung next symbol niyan should start with 1 1 1. Okay? Now, so we'll assign A4 to 1 1 1 0. And then since isa na lang yung naiiwan, then let's switch yung 0 dito to 1. So that we assign A5. This is A5, sorry. So this is A5. Okay, let's assign the message A5 to the symbol 1 1 1 1. Okay, so this will now be the code, okay, that we have constructed. Okay, so the question is the code compliant or does the code word length of code A satisfy the Kraft inequality? So tingnan natin. The code word lengths here are 1, 2, 3, 4, and 4. So therefore, to compute the Kraft number for code A, okay, we will have the summation of 2 raised to negative n k, okay, for k equals 1 up to L. So, yun na nga, isa-isa lang natin to. So, this is 2 raised to negative 1 plus 2 raised to negative 2 plus 2 raised to negative 3 plus 2 times 2 raised to negative 4. Okay, kasi dalawa yung 2 raised to negative 4. Okay, so when we calculate the Kraft number for code A, we find that that Kraft number is equal to, okay, so this Kraft number is equal to 1. Okay, so therefore it satisfies the Kraft inequality. So this is equal to 1, which is less than or equal to 1. So therefore Kraft inequality is satisfied. Okay? So, it means that for this given set of code word lengths, okay? For the given set of code word lengths na 1, 2, 1, 2, 3, 4, and 4, given yung set of code word lengths na yan, possible that a code satisfying the prefix condition can be synthesized. So, possible yon. Pero again, the design of such codes, okay, or what those codes are, is another matter. Pero dito naman, dahil dinesign nga natin yung code natin in this manner, okay, ensuring na walang magiging prefix condition kasi nga pinipili natin yung mga symbols natin in such a manner that they cannot be a prefix dun sa mga susunod na longer codes. Okay? Then we have ensured, or we ensured ourselves that code A satisfies the prefix condition. Okay? So, yun. Now, let's take a look at code B. Kasi yung code B naman, kung papansin niyo, also complies, hiwalay natin siya. Okay, so notice that code B also satisfies the prefix condition kasi wala tayong makikitang shorter code being the start or the prefix of the longer code. For example, yung 00, hindi nyo makikita sa dalawang code na to. Or yung 01 cannot be seen in any of this 2, 3 binary digit code. Or kahit yung 10. So, wala tayong, these shorter codes are not a prefix of the longer codes. Okay, so this satisfies, okay, this code, so code B, satisfies the prefix condition. Okay? But if we take a look at the set of code word lengths for code B, so we have 2, 2, 2, 3, and 3. Iba siya dun sa set of code word lengths para sa code A, which is ito, 1, 2, 3, 4, 4. So sa code B, we have 2, 2, 2, 3, 3. So if we actually compute the Kraft number for code B, okay, which is the summation of 2 raised to negative nk, okay, for k equals 1 up to L, we will have 3 times 2 raised to negative 2. Kasi tatlo tong code word length natin na 2. Okay? Plus 2 times 2 raised to negative 3. Kasi dalawa tong code word lengths natin na 3. So pag kinompute natin ito, okay, itong Kraft number na to, this results to a Kraft number of 1. Okay? So, a Kraft number of 1, meaning, nasasatisfy niya rin yung Kraft inequality. So, Kraft inequality is satisfied. Okay? So, again, nasatisfy natin yung Kraft inequality using this set of code word lengths. And, yung mismong na-design na code para sa code B, satisfies the prefix condition. Okay? So, again, reminder, the Kraft inequality only tests whether it is possible to come up with a code that satisfies the prefix condition. Okay? But the design of such codes is another matter. Okay? So, kahit na yung set of code word lengths mo is compliant with the Kraft inequality, kung mali talaga yung design ng code words mo, okay, then pwede pa rin mag-violate ng prefix condition yung codes mo. Okay? So, here, we state another version of the lossless source coding theorem. Okay? Now, this time, number one, this version of the lossless source coding theorem applies to codes that satisfies the prefix condition. So, kailangan we apply this to all those codes that satisfy the prefix condition. Okay, so here let X denote a DMS with finite entropy H of X, okay, and output letters AI for I between 1 and n, okay, with corresponding probabilities of occurrence Pi, okay, again I from 1 to n. Now it is possible to construct a code that satisfies the prefix condition, okay, and has an average length of R bar, okay, that satisfy this inequality. Okay? So, kapag we interpret it as follows, okay? Specifically, this applies to to codes that satisfy the prefix condition. Okay? Um, we also specify the limit of the transmission, okay? Of the amount of information in terms of the code word length R bar, okay? Instead of the transmission rate R. Okay? So um ngayon, we can consider, okay? We can now consider na in our next lesson na ang gagawin natin ngayon is instead of actually specifying the limit or the compression limit for our source codes, okay, as the transmission rate R, okay, we instead specify this compression limit in terms of the average code word length, which is specified as R bar. Okay? So, ngayon, yung limit ngayon ng ating transmission, or transmission would only happen, okay? And decoding is possible, okay? If R bar is between the values of the entropy of the source and the entropy of the source, okay, plus 1. So, ito yung lossless source coding limit or compression limit natin for specified in terms of the average code word length. Okay? So, there. So, this ends the lesson on lossless source coding theorem. Okay? In the next lesson, we will discuss the formal algorithms that are used to synthesize variable length codes and fixed length codes for your source for your message sources.